So today I'll be talking about enthalpy, heat capacities, and I'll be going on talking about the first law, means and enthalpy, heat capacity, and slowly we'll go into the second law. So remember, we talked about first law, and we have already given a statement of first law in the differential form. This is like delta u du equals delta q plus delta w, and you can write it in the integral form, means in a mode. So that becomes like, this is the differential form. Again, these are path differentials, as you can see here, but these are path differentials, and if I do this, delta u equals to q plus w, right? And this is called the differential form. This is the differential form. And this is something that you get after integration. So when you do integration, for example, u is a state function, so you are integrating between the initial and the final state, or between two states, so you get delta u, and q and w again depends on the path, right? So we said this is basically, we can call it like, this is more like a integral form, or we can call it like the means where you have done the measurement over say two states, right? This is like that. So it is after integration, right? So this is the integral form. Now, as I told you, so when you have a closed system, then energy transfer is something that is allowed, right? Energy transfer between the system and surroundings is allowed, but the wall is impermeable. Although the wall is diathermal, right? Diathermal means allows heat transfer and exchange between the system and surroundings, but it is impermeable. That is, it does not allow exchange of matter, right? So in such cases, for closed systems, this is the first law. Now, what about open system? Open system means, for example, I have taken this system. This is my system boundary. Please understand, this is my system boundary. This dotted lines represent my system boundary, and there is some substance that is pushed in and substance that is pushed out, right? Matter pushed in, matter pushed out. So basically, this open system allows exchange of matter as well as energy. So it is allowing exchange of matter as well as exchange of energy, right, across the boundary. Now, in these cases, when you have such a system, a steady state, for example, steady state means we are not talking about any rate of accumulation or stuff. So then we have to include something called flow work, because you are pushing in some matter here, you are pushing in some matter, you are taking out some matter. Okay, it can be like some fluid, some solid, whatever it is. Now, when you are pushing in some matter, obviously you are putting some, means if you are pushing in some matter, then you are applying some pressure on it, right? And you are taking out some matter, then basically again it is you are basically, when you are forcing, then you are putting a force on it or pressure on it, and when you are taking it out, then you are relieving some of the pressure. So that is how we can think of it. So this work that happens is called flow work. Now, for example, we tell that the amount of substance that the substance that comes in, I specify using something like V in. V in is the volume input, and our volume at the inlet of that substance that you are pushing in, and M in is the mass of the substance that you are pushing in, and again V out and M out are the volume of the substance that you are pushing out, and volume of matter that you are pushing out, and M is the mass of matter that you are pushing out. So basically, now as you can see in the open system, there is some mass pushed in, or some matter pushed in, which has some mass, and some matter pushed out, right? So in that open system, although it has all these other things, that there is an internal energy like U, and then there is also, you can have some other processes, but there is also this process where you are pushing in some matter and taking out some matter, right? So you are taking out some matter and you are pushing in some matter. Now, in such cases, if you have such an open system, we can think of, there is a pressure at the inlet and there is a pressure at the outlet, which is again related to the flow work, and we can call, so now we can think of a specific quantity, which is basically volume per unit mass input. So that means your the M in is the mass at the inlet, right? Mass of matter that is pushed in the open system. Now V bar in is a specific quantity, right? It's a specific quantity per unit mass or per unit mole. So, and what we are doing? V bar in is nothing but V in by M in, right? And similarly, you can have V bar out, which is V bar out will be V out by M out, right? So there is a flow work in and there is a flow work out, and we call it WF in and WF out. Now you see, when you are pushing in some matter, you are applying some pressure P in, right? So there is a P inlet. So you can call it P V bar delta M, or dm is a basically a state function. So I can replace this with d P V bar dm, which is basically, so P V bar dm, so P dv. So what I am doing is I write this P dv, right, where P is the P in, say, and then there is dv, and dv, so what I am doing is I am writing dv equals to V bar dm, right, V bar dm, because V bar is volume per unit mass, right? So P V bar dm, which is delta Wf, right? That's the flow work. Now P V bar dm is positive when matter is entering. When matter enters, P V bar dm is positive, because it is what you can think of it as like some work done on the system. And when P V bar dm is coming out, that means matter is coming out, then P V bar dm is negative, right? So because what is coming in we are taking as positive, that's convention, and P V bar dm out we are taking it as negative, right? Again a convention. So whatever is coming in is basically giving you a positive contribution, coming out is giving you a negative contribution. So if I now do this, I have Wf in, which is P V bar in dm, and dm in this is, and P is constant inlet, let's call it P in. So basically if you look at this integral, so P which is constant the inlet is P in, so I take out P, so P in, V bar in also I can take out, and dm in I am taking from 0 to m in, right, because it was initially nothing was there, and then I have pushed in some matter, so 0 to m in, and so 0 to m in means basically it will be plus P in V bar in m in, that is my Wf input, right, the flow work that is input, and the flow work that is output will be minus P out V bar out m. So if that is so, moreover the matter that we are pushing in has some internal energy. Again I can define something like U in by M in, which is nothing but U bar in, which is specific, it's like a specific internal energy per unit mass entering the system. Similarly, U bar out will be the specific internal energy associated with the mass that is leaving the system. So this is specific internal energy associated with the mass that is entering, this is the specific internal energy associated with the mass that is leaving. And then you have delta Q, which is plus U in dm in, and then you have minus U out dm out, and you also had delta Wf in, the flow work input, and then the flow work output, which is P in V bar in dm in, P out minus P out V bar out dm out. So whatever you can see, that sign convention that is followed is anything that is coming in corresponding to the same closed system convention that we followed, that heat input is positive. Similarly, the flow work that involves matter coming in, and along with the matter, the flow work that is done to push the matter in, and the internal energy associated with that matter that is pushed in, all of these we are taking as positive, and whatever is leaving the system we are taking as negative, right? We are taking as negative. Now, so if I have to now balance the energies, what I get is du. Du is the change in energy. It's an infinitesimal change in energy, in the open system, right? It's a change in energy, internal energy. Again, it's an infinitesimal change in the open system. So, this change in internal energy is equals to delta Q in minus delta Q out plus delta WF in minus delta WF out plus delta Q plus delta W, that is the heat input to the open system, and delta W is the work done on the open system or work done by the open system. It can be on or by, and depending on it we will put a negative sign or a positive sign. Now, so if you have that, one interesting part of it is that before I go to enthalpy, I want to tell you this. In the flow arc that is coming in, you have U bar in, right? That is the U bar inlet, and you have U bar in plus P in, V bar in, right? Dn in, right? That's how it is. And then you have minus U bar in plus P, sorry, this is minus, right? So it is going out, U bar out plus P out, V bar out, Dn out. And then you have your delta Q and then W, which is equal to. Now, if you look at this term, you have this term which is like U plus PV, right? And this is the term that you have, like U plus PV is coming in and then U plus PV is going out. So it's like U plus PV in and then there is a U plus PV. Now this I can call as, in some way, this I can call as some H in and H out. I am just putting some new variable here. Okay, now what is this H? So I will define this H as enthalpy. So this, now if you look at, so it's enthalpy, which is H. Now why is this enthalpy required? Because if you see, we know from the first law for a closed system cell that du is equal to delta Q plus delta W, and that is basically equal to delta Q minus PdV. Now minus PdV, because if you are say basically compressing a gas using a piston, if you are compressing a gas using a piston, you are compressing it with a pressure, then there is a change in volume, right? There is a change in volume, that dV is negative, and you want work done on the system here always assuming as positive, right, in our convention. So we put a minus sign here. Okay, so you can understand that du equals delta Q minus PdV. By the way, if you use another convention, you will get back the same minus PdV, because in that case work is done against the external pressure, right? So in such a case where the volume is increasing, when the volume of a gas will increase, say for example, it is work done against external pressure. Here we are doing external pressure is doing the work on the system, but in that process dV is negative, so therefore I have to put a minus sign. So in both cases it is consistent. Now what you get, but that's not the matter here. The matter is more interesting here, that you have a delta U, which is Q is the heat input, remember, Q is the heat input, minus P delta V. So now you will tell, is this correct, minus P delta V? There should be a V delta P. So I assume, so for example, that's why I gave a blank here. So we are talking about constant pressure, and we are looking at energy balance at constant pressure. Now if you are looking at constant pressure, then basically you will see delta U is nothing but Q minus P delta V. Okay, so this is done at constant pressure. So Q becomes delta U plus P delta V. So it is something either more or less than delta U. Now can you tell me, so this is something that you can think about, that Q is the heat input, right? Q is the heat, you can think of it as heat input. Now depending on whether it is negative or positive, we can tell whether heat is going out to the surroundings or whether heat is entering the system. And delta U is the change in internal energy. You see, unless it's a constant volume process, in that case delta V will be 0 because the volume will not change, then only Q equal to delta U. Other than that, Q is equal to delta U plus P delta V. Now, depending on P delta V, delta U can be more than Q or delta U can be less than Q. Or is it that always Q is greater than delta U by an amount? Q differs from delta U by an amount P delta V. And to absorb this P delta V, we use a new thermodynamic potential called enthalpy. I will later tell you that how these different thermodynamic potentials basically come from doing these Legendre transforms, how they are related. Basically, these are like conjugate variables. You will see different conjugate variables like entropy and temperature, volume and pressure, chemical potential and concentration, and so on and so forth. But what I am trying to say is that you can immediately see the need of, at constant pressure, you have Q, which is not just delta U, but Q, which is delta U plus P delta V. So now, to make our life easy, we define so every time we define a new state function in thermodynamics, you remember, we want to simplify our understanding or simplify the description. So we define this new state function called enthalpy, which is U plus PV, right? PV is the mechanical work, quantity related to the mechanical work, and U is the internal energy, and H is called enthalpy. As U is extensive parameter, V is extensive parameter, H is also an extensive parameter, extensive variable, right? It's a extensive variable. Similarly, U is a state function, V is a state function, so H is also a state function, right? It depends on the states only. It does not depend on the path, right? Finding H, I don't, when I want to integrate, I have to know the initial state and the final state of the system. I don't have to know in which path these states are arrived at, right? So an H bar is specific enthalpy. Specific enthalpy can be enthalpy per unit mass or enthalpy per unit mole, and we can call it H bar or HM. So I will use either H bar or HM in this course, right? So this is the enthalpy per mole. It can be enthalpy per mass. Okay, so every time I will specify whether it's molar enthalpy or it is per unit mass. Now, what we told is that's a constant pressure. Now, why do we tell that? Because you see H equals to U plus P. Now, if I differentiate, I get dH, which is du plus pdV plus vdP. Now, this only becomes du plus pdV when dP equal to 0. That means constant pressure. So, you see now, du is equals to delta Q plus delta W, which is delta Q minus PdV, and as you can see, dH is du plus PdV. So from here you can write delta QP equals to du plus PdV. So I gave a suffix P, right, subscript P, I use this subscript P to denote that it is at constant pressure. So dH is equals to delta QP. That means heat input at constant pressure. So in general, as you can see previously, we wrote du is equals to delta QV, which is at constant volume. This is constant process, because if it is constant volume process, then delta V is 0. So in the constant volume case, you have du equal to delta QV, and when it is constant pressure, I am now differentiating you see dH equals to delta QP. So as you can see here, this is at H is thermodynamic potential that we will use when we are looking at processes where the pressure is constant, right? So something like that. So we will come to see that more. Now if I look at a measurable change, again I am integrating between the states. So basically, and delta H, basically delta H is equals to QP, that is heat input at constant. This is heat input at constant pressure. If this heat input at constant pressure changes my system from initial state I to a final state F, then the difference HF minus HI, which is basically you can express it as delta H, this is a measurable change. Delta H is a measurable change. So please note this, that D of something, say D of Z, is a infinite symbol change, right? It's a differential. But when I tell delta of Z, it's a measurable change, right? So which is basically like ZF minus ZI, where F and I denote the two states, and DZ basically is a differential. It's a differential change. And I have also told what is an exact differential instead. So in constant volume, as I told again, it's du, and at constant pressure it is dH, right? So now at constant pressure one can write dH equals to, as I told, dH equals to du plus PdV, and if you now integrate, what you get is delta H equals to delta U plus P delta V, because delta H is HF minus HI, delta U is EF minus EI, and delta V is UF minus V. Now let us look at a problem. We will try to look at a problem and we will see, because enthalpy is something very interesting in a constant pressure process. Many times we use like heat, means when we express like heat of reaction or heat of change of phase, say from solid to liquid or liquid to solid or solid to gas or liquid to gas, and some such processes like evaporation, condensation, solidification, melting, we will use delta H. We also use delta U if the processes are constant volume. Otherwise, at constant pressure, we will always use enthalpy, right? We call it like transformation enthalpy or enthalpy of formation and stuff. So here, for example, I given a problem here, which is enthalpy of fusion. Now, enthalpy of fusion means fusion is nothing but melting. So, of ice at 0 degrees Celsius. Remember, ice and water are two phases or two states of H2O, right, of water. So liquid water and ice. So at 0 degrees Celsius, both ice and water can coexist. Now enthalpy of fusion, that is it's like latent heat. Okay, enthalpy, often we call it as latent heat also, of fusion of ice at 0 degrees Celsius and 1 atmospheric pressure is 6 kilojoules per mole. That means you have to supply 6 kilojoules per mole of ice to melt it at 0 degrees Celsius. Now you see another very interesting thing, molar volume of ice at 0 degrees Celsius is 0.0196 liters and of water is 0.018 liters. You see, this is liquid water. Remember, ice is the solid form of water. This is the liquid water. Let's call it liquid. So water in the liquid form and ice is water in the solid form. So if you see, the solid form has a higher molar volume, 0.0196, and water has a molar volume of 0.018. Okay, at 0 degrees Celsius. Again, this is measured at 0 degrees Celsius. Now I am telling, find delta H and delta U. Find delta H and delta U of fusion at 0 degrees Celsius. Delta H of fusion I have already given, 6 kilojoules per mole. Now we have to see whether it is positive or negative. So let us look at it. So the process is ice melts to ice is melting to water, right? Now there are two types of processes that generally we know. You might have also read about it in your 12th standard textbooks or 11th standard textbooks, that you have this endothermic process and exothermic process. Endothermic process is where heat is absorbed by the system and the heat is coming from surroundings. So basically, when heat is absorbed by a system, then and from the surroundings, it is entering from surroundings and it is getting absorbed by the system, then you have something called an endothermic process. And where heat is released or heat is evolved by the system and is released to the surroundings, basically, then it's called an exothermic process. Okay, so exothermic process, there are two types of processes. One case it is absorbed, okay, and another case it is given out. So for example, when I am looking at melting, ice melting to water, in that case ice requires heat input, so it absorbs heat and then it melts to water. On the other hand, if water freezes to ice, when water freezes to ice, it gives out heat, right? It gives out the enthalpy of fusion. Now, when it is giving out, as you know, in the endothermic process, heat is absorbed by the system or heat is input to the system, right? So here, what you can tell is basically heat input to system is positive. On the other hand, when it is an exothermic process, system is giving out heat, right? So it is like heat output from the system. So heat input in that way is negative because heat is extracted out of the system, right? Or heat is evolved. It's not really extracted. It's released from the system to the surroundings. So heat input to system in this case is negative, right? So basically, because the system is giving out heat to the surroundings, right? Now, when surroundings is giving heat, then ice transforms to water. So ice absorbs heat, right, from the surrounding. So it's melting is an endothermic process. Freezing is an exothermic process. So at 1 atmosphere, as we see, 1 mole of ice requires 6 kilojoules of heat. That means it requires 6,000 joules. Now we also know the molar volumes, right? Molar volumes of water and ice. So as we know, Q basically is nothing but delta H here, because we are keeping the pressure at 1 atmosphere, right? Pressure is fixed. So you have delta H, QP, that is the heat input at constant pressure, which is delta H or heat of fusion, and this is given as plus, so it will be plus 6,000 joules, right? So delta H equals to 6,000 joules. Now I have to find out what is delta U of the process. I have to find out what is delta U. Now we know the relation delta H equals to delta U plus P delta V, and we know the molar volume of ice, which is 0.0196, and this is 0.018. So now remember, 1 liter is 1 decimeter cubed. So this is something that you have to know the units. 1 decimeter cubed is like 1 decimeter is like 0.1 meter, right? So you have decimeter cube, so you have 0.001 meter cube, and 1 atmosphere is 101,325 pascals. Pascal is the unit of pressure, right? Pascal is Newton per meter square, and 1 atmosphere is also unit of pressure, but 1 atmosphere means 101,325 pascal. Now delta V is what? It is final state is water, liquid water, and the initial state is ice. So it will be V water minus V ice, right? V water minus V ice. And we are looking at only 1 mole of the system, so we are taking the molar volume of water here at 0 degrees Celsius and this molar volume of ice. And what do we get? V water minus V ice is negative, right? It is negative, right? And it is like minus 1.6 and 10 minus 3 liters. And P is 1 atmosphere. So P delta V, if I now convert atmosphere liter to joule, you have to multiply with 101.325. This is because 1 liter is 0.001 meter cube and 1 atmosphere is 101.325. If you multiply, you get 101.325 as the conversion factor. So if you use 101.325, you get a value which is, as you can see here, minus 0.16212 joules, which is quite small. It's very, very small. See, 6000 joules is the enthalpy of fusion, and P delta V term is only minus 0.16212 joules. So as you can see here, delta H is 6000 joules, delta U is going to be 6000 minus of 0.16212, or this is 6000.16212 joules. So delta U is slightly more than delta H, but it's not really that much different. So we get delta U to be approximately the same as delta H. Remember, I haven't given I have given a working definition of phase, but I haven't given the proper, means the definition that is accepted in textbooks and stuff. But phase, basically, see, for example, ice and water, these are two states of matter, and these are like, you can call them as like two phases, because they have their own physical characteristics, like distinct physical characteristics, and they have also chemical composition, right? In both are like H2O, right? And H2O means basically one component. I can think of water as H2O as one component. These are like unary systems, consider water as a component. And these are phases with physical characteristics which are distinct, and they are also mechanically separable. So I'll come to this mechanically separable stuff in a while. So when I give a more, when I look at different the equilibrium between phases in a short while. So these are mechanically separable, these are physically distinct, and they should have uniform chemical composition, right? That's the idea. So the idea of mechanically separable is interesting, and I'll talk about like mechanically separable means by some such process, right? So but there is a little bit of confusion there, and I will come to that, where it can be, sometimes it can be confusing, but anyway, the point that I want to tell, phase, ice is a phase, the solid phase of water, liquid water, and water liquid is also another phase. The solid phase has different property, like different molar volume, different density. Water has different property like molar volume, density, refractive index, whatever it is, and both are condensed phases. How? Condensed phases means they are, I'll talk about this, their compressibility, like it is not as compressible as gas, right? So water or ice are not as compressible as gas. Gas is much way more compressible, right? So in case of ice and water, both are called condensed phases. Means basically the PV work in condensed phases, condensed phases is like solids and liquids. PV work is negligible. So again, I'll just give a working definition of phase. If you missed it, a phase is that portion of matter or phase is a portion of matter or region of matter or region of space containing matter. So is that portion of matter which is chemically homogeneous, physically distinct, and mechanically separate. For example, I have a system where you have this ice and you have water. So see, there is a clear boundary between ice and water. Although both are H2O, one is in the solid form and another is in the liquid form. They have different densities, they have different molar volumes, they have different refracting indices and so on and so forth. They are physically distinct. And both ice and water are chemically homogeneous, right? So as you can see, these are the phases. So this is again an ice cube, right? So ice and water is one example that I can talk about where I have two distinct phases. Liquid water is a different phase, ice is a different phase, right? So, but you see that ice and water both are condensed phases. PV water is negligible, right? Because the volume change with pressure is very, very small. You have to give enormous pressure to see appreciable volume change. As much volume change as you see in gas, you can't get unless you give a really, really enormous pressure. So PV work is negligible, but I will come to this PV work soon. Now think of another reaction. So to understand the concept of enthalpy, right, we think of a reaction where you have gas involved. So for example, we are thinking of combustion reactions. Now in combustion reactions, you think of combustion. What do you think? You have fuel. That fuel can be liquid or solid. It can be gasoline. It can be coal, coke. It can be like some pure form of graphite, whatever it is, and you are putting oxygen. You are giving oxygen, and this graphite is burning. Graphite and oxygen graphite burns in oxygen, and it gives you carbon dioxide. Right? This is the reaction. C plus O2 equal to CO2. Now, when combustion happens, in general, it will produce heat. That's why we do use combustors, right? You want to produce heat. If you want to produce heat, for example, you take wood and you put fire, and you want, means when you want to have fire, then what you do? You basically involve oxygen in it, right? Without oxygen, the fire will die, right? So the burning will happen if there is oxygen, right? So carbon plus oxygen goes to carbon dioxide. Now this reaction or these combustion reactions, all combustion reactions produce heat, right? You will produce heat. So heat will be released to the surroundings. So as a result, it will be exothermic, and that means heat input is negative because heat is released to the surroundings, right? It is, as you can see here, it is released to the surroundings when this reaction happens. In the forward, right? Carbon solid, which can be coke, which can be graphite, pure form of carbon, graphite, and that is reacting with oxygen, forming carbon dioxide, and this is producing heat, and this producing, because it is producing heat, we call this reaction a combustion reaction, right? So all reactions where you burn fuel to produce heat are called combustion reactions in presence of air. Right? Air basically helps in burning. Now we are thinking of our temperature of, so the burning here or combustion is happening at 298 Kelvin. See, the temperature that you have, it's like room temperature, 25 degrees Celsius, 298 Kelvin, and you have 1 atmosphere pressure, and in that temperature and pressure, molar volume of graphite is 0.0053 liters, which is quite small, right? If you look at molar volume of gases, remember at STP, you might have read, which is like 0 degrees Celsius, 1 atmosphere pressure, the volume is 20.4 liters for ideal gases. Again, if you assume oxygen and carbon dioxide to be ideal gases, you can basically get the volume of 1 mole of a gas. So R is 8.314 joules per mole Kelvin. You have PV equals to nRT, N equal to 1 because you are taking 1 mole, say, and then V is this 8.314 into 298 by 101325, because see, V is equals to nRT by P, and P is 1 atmosphere, which is 101325 pascals or Newton per meter square. So what you get is 0.02445 173 meter cube, which is 24.45 liters. So as you can see here, 24.45 liters is the volume of the gases, oxygen or carbon dioxide. On the other hand, the molar volume of graphite, that's for 1 mole of these gases. On the other hand, the volume of graphite, 1 mole of graphite is 0.0053 liters. You can see how much the volume differs for 1 mole. And now let us look at, we understand that volume does differ. But see, ultimately, if I give an ideal gas assumption, I will use only the gases. C plus O2 goes to CO2. So what is the delta H reaction? It is given as minus 394 kilojoules per mole. Right? So it means it gives out 394 kilojoules of heat. It gives out 394 kilojoules of heat. This reaction, C plus O2 CO2, and at room temperature and pressure. Now, this is minus 394 kilojoules of heat per mole. Now, we are assuming oxygen and carbon dioxide to be ideal gases. And that means they follow this equation of state P equals to nRT. And we know H, which is U plus PV. Now, instead of PV, I write U plus nRT. Now, you have dH, which is du plus dnRT. R is gas constant, it's constant, you can take it out. Now, you have RTDN, right? Because it's like R, D, and T, and this will be R, D, N, and there is a T plus N, R, D, right? So this is what it is. So you will have these two terms, RTDN and RTT, but as you can see here, it is constant temperature 298 Kelvin, right? It is 298 Kelvin, constant temperature T2 is 0. So this becomes du plus RTTN. Now dH equals du plus RTTN. Now I can now integrate. So in a measurable form it will be delta H, right? In the finite form it is delta H equals to delta U plus RT delta N. The reaction is C solid combining with oxygen gas to give carbon dioxide gas. N before reaction. Now if I am looking at the N, I am not caring about the N of graphite, right? I don't care about graphite. So I will look at the N because I am using PV equals to nRT here. So I look only at the gases, participating gases, O2 and CO2. See, this is like 1 mole of gas if you look at the balance, and this is also 1 mole of, it produces 1 mole of, so 1 mole of oxygen reacts with 1 mole of carbon to give 1 mole of carbon dioxide. So N of gas before reaction is 1, after reaction is 1, delta N, which is product minus reactant, is 0. So delta H equals delta U plus 0, and delta H minus 394 kilojoules per mole. So delta U equals to delta H minus RT delta N, and therefore which is equal to 0 here. So delta U equal to delta H equals to minus 394 kilojoules per mole. So, and as you can see, moles of carbon are not considered. So even in this case where gases are involved, you could see very interestingly that the change in internal energy and change in enthalpy means that is basically coming out to the same. Obviously, if you have a reaction like, say, for example, you can do it yourself. Say I am talking about, say, N2 plus 3H2 equal to 2NH3. Now in this case, this is gas, right? This is gas, and this is also gas, right? In such a case, and you can see here 1 mole of nitrogen, 3 moles of hydrogen, and 2 moles of ammonia. These are some cases where you will see that there may be some difference between delta U and delta H. Basically, find out examples. You can find out examples where delta U and delta H are different, right? So please think about it. Think about different reactions. I will also give some examples later. Now I will come to a very important quantity called heat capacity. I will come to a very, very important quantity called heat capacity. And heat capacity is basically the amount of heat or thermal energy required by a substance, right? Heat capacity of a substance or a material is the amount of heat or thermal energy required by a substance required by a substance to raise the temperature of this material or substance by some amount, right? It is not specified, right, in general, but we will by convention use like by 1 degree Celsius or by 1 Kelvin. Now, or by 1 degree Fahrenheit, say for example. Now, I haven't even yet defined the Kelvin scale, but I am telling because you already know about Kelvin scale. So, there are different types of temperature scales that you know like there is a centigrade scale, there is a Fahrenheit scale, and there is also this absolute scale of temperature. Obviously, how does it come? We have to cover it, but before that, what we understand is heat capacity. Heat capacity is a very, very important property of matter. Now, what we can write is, so this is the amount of heat or thermal energy. So that means this, you can write some relation like this is something that you have often seen. This delta Q, which is equal to CdT, right? So basically, C is a ratio between delta Q and dT. That means heat input and changing temperature, right? Now, if you think of this, in general, if you have a heat input to a system, the temperature increases. So, you will have typically curves like this. This is the curve U versus T. So, U increases as T increases. And if you now draw, if you take one point here, say here, you draw a common tangent line. So, this is your common tangent line. You can now take the slope at that point. So, this will be like you have this is delta U, this is delta T. So, the slope is limit delta T tends to 0, delta U by delta T, or you can also write this is equal to du by dt. Right? Now, this basically gives you C. Now, is it always du by dt? We'll come to know. So, you see, no, at constant volume, it will be CV. Okay, that means this is heat capacity at constant volume, which is delta Q, which is delta QV by delta del T or del U del T V. Remember this. This is very important. Del U del T at constant volume, right? It is constant volume. That is CV. Now, when you look at constant pressure processes, again, what comes in is enthalpy, not U, right? Because you have enthalpy, right? At constant pressure, as you know, delta H is delta U plus P delta V. So, there is this P delta V1, right? For example, think of this gas enclosed here and you are having a piston that is just coming in. Now, you are seeing that there is a heat input and there is a pressure, you are giving a pressure and the volume is changing. So, all of these contribute to the heat capacity at constant pressure, right? You have pressure volume work as well as heat input, and that both of them are contributing to the constant pressure process, right? So, at constant pressure, we have to look at how H varies with temperature. You will get essentially a very similar curve. H will increase as a function of temperature, right? In general, H will increase as a function of temperature. In that case, again, whether it is increasing or decreasing is the slope, right? It is delta H by delta T. Again, with delta T tends to 0. So, this basically gives you delta QV by delta dt, or you can think of this as del H by del T at constant pressure. So, as you can see here, Cp is del H by del T, right? Cp equal to del H by del T. So, again, just recollect that we talked about exact differential, we talked about z equal to zxy, and if z is an exact differential, it is m dx plus m dy. M is del z by del x with constant y, and n is del z by del y constant x. And you have also this del m by del y equals del m by del x, which gives rise to this, and these will be used to find some relations called Maxwell's relations. Or Maxwell relations. I'll come to that, but before that, come to this second derivative, because remember, when we write Maxwell relations, we are basically relying on this relation del m del y and del m del x, which basically gives you second derivatives. Right? These are the second derivatives. Okay, but see, this exact differential gives you m and n. Now this m and n, say for example u, if I write as a function of t and v, I get del u del t v dt plus del u del v t dv, right? So del u del t v at constant volume, this is del u del v, that is the changing internal energy with changing temperature at constant volume. This is changing internal energy with changing volume, changing internal energy with changing volume at constant temperature, right? At constant temperature. So you get Cv dt and you get some coefficient like del u del v t, which is pi t dv. So, but at constant, if you think of constant temperature, then du, you know, is minus p dv, right? Because du is delta q. Say for example, I can write this du is equals to delta q minus p dv. Now delta q I can write as C dt minus p dv. C is the heat capacity. Now I can take dt equal to 0, that means at constant temperature, then du is minus p dv. Now have a look at this. Now you have del u del t v, which is Cv, right? Del u del t v, that is the change in energy temperature at constant volume, which is Cv. And here you have pi t, and if you look at this relation, here du equals to minus p dv, and here this pi t is obviously having a unit of pressure, right? And this pi t, this coefficient is called internal pressure, right? Pi t is basically nothing but minus p, if I compare that. So du is Cv dt plus pi t dv, and du equal to Cv dt minus p dv. So as you can see, pi t is minus p, which is the internal pressure, right? So, however, remember, you don't have, in fact, you can show it later, but now please understand, if there is no interaction between molecules, that is, there is no force of interaction between molecules, then p dv, which is nothing but force of interaction with the, so this is an interaction force, and this is the, I can think of like separation distance between particles or molecules. Then this p dv term or this internal interaction term basically goes to 0. This is not an external pressure. Remember, this is the let's not call it. Let's call it pi t, and pi t is the internal pressure which arises due to internal forces of interaction between the molecules. And if there is no force of interaction between molecules, for example, in ideal gas or perfect gas, okay, so R is like an interaction distance between these particles or molecules or atoms. Now, if F interaction is 0, then pi t comes out to be 0. So, this is a very, very important conclusion. So, as you know, equation of state PV is nRT, and you have CV, which is del u del dV, right? Say del u del dV, and Cp, which is del H del dV. We will try to find relations between them. We will also try to find, not only find the relations between them, but we will also try to find out more measurable quantities that you can define, like temperature, pressure. You have already looked at different variables that we can, so what variables so far we have learned that are measurable directly, like T or temperature, which is measurable by a thermometer, then you have P, which is measured by a barometer, and then you have Cp and Cv. These things you can measure basically using calorimetry. Okay, you can use calorimeters to measure it. So I'll give you some principle, means how it is done. The principle is based on what I have taught, right? It's basically the first law is what you will use. So, so you use calorimetry to find out Cp, Cv. So these are measurable quantities. Temperature is a measurable quantity. Pressure is a measurable quantity. Volume, again, if I know the dimensions, I can calculate volume. Measurable quantities. So we are getting a bunch of measurable quantities. I'll also give some more measurable quantities, and we will try to find out interrelations between them. Right? That's something very, very important. When you want to organize data and all, you require all this thermochemical data consistently. Then only you can give an energy description of matter. So this is something that I'll deal with in the next class. Thanks for your attention.